in the role of A in this. And the conclusion of this case was that A equals B, which means that A equals plus or minus B. Okay? So the conclusion of this, sorry, this implies, yes, I left out that step. Okay, so A equals B. I said it, but I didn't write that down. So maybe that clarifies it. Minus A equals B. Okay, does that clear that one up?
I believe so.
Okay. So then we get a corollary of this. The only integers that divide 1 are what? Yeah, plus or minus 1. Okay, any questions about this? So this is sort of a new way to show that, and believe it or not, this actually could be useful, right? But this is a way to show that A equal plus or minus B, or if they're natural numbers, that A equals B, just to show one divides the other and vice versa. Then you get that if they're natural numbers, they have to be the same. All right, next what I'm going to do is define a set that's actually very useful. We won't do quite as much. You'll have some exercises involving this. We won't do quite as much with this in this class, but if you're a math major or math minor, you're going to be taking an algebra class, abstract algebra class at some point. And this sort of arguments that we use here are going to be very important in that class. Okay, we're going to prove some things about this set that you will see later. So we're going to let A be an element of Z. Define AZ equal the set of all M an element of Z such that A divides M. Okay, so you're wondering, why are we calling this A times Z? Why is that the notation we're using, right? Well, can anybody say how to rewrite this thing? What does A divides M mean again?
M equals CA.
Yes. So remember, this means that M equals CA for what?
Some C element of Z.
Yes, C an element of Z. So we can rewrite this as the set of all CA such that C is an element of Z. Or actually, I'll reverse that and call it AC. How about that? So you see why this is called AZ. I mean, this is only notation. I'm not proving anything here, but this is why we give it this name, because it's all integers multiplied by A, basically. So for example, what is 2Z? You have another name for that.
Even numbers?
Yes, is the set of even integers. All things that are divisible by 2. And again, to us, it does not mean that you can divide it by 2. because you can divide anything by 2. The point is that you can divide it by 2 and get a natural number, but that's again not a good way to think about it. Now this is quite an interesting set, actually, from the standpoint of abstract algebra. The integers are something called a ring, and a ring is just a system of things that has an addition and a multiplication. So it's just like a field, except you don't have the commutative axiom necessarily, and you don't have multiplicative inverses necessarily. All right, but you do have the distributive law, associative law, and those kinds of things, right? Okay, so what we're going to be showing here is, in effect, that this thing is a subring, meaning that it's closed under multiplication and addition. So it's its own little ring, right? So for example, if you just took the set of consisting of 0, 1, and 5, that's not closed under addition or multiplication, right? You have to go outside the set when you multiply 5 by itself or add 5 to itself. So what we're going to now show is that this set that we've defined is actually closed under multiplication and addition. So for any A an element of Z, AZ is closed under multiplication and addition. By the way, if you've had matrix algebra, how many of you have had matrix algebra, by the way? Oh yeah, everybody or almost everybody? Okay, so how many of you have not had matrix algebra? Okay, our lone non-matrix algebra. Okay, right. But if you've had matrix algebra, then you've already done this, right? You've already shown, unless you had a lousy course in matrix algebra, you have shown that something is a vector subspace. Right? So a vector space is another one of these abstract algebraic objects where there you have an addition and you have scalar multiplication, but you can't multiply vectors, at least in general. I mean, you can do it in some special cases. You have dot products and cross products, right? But okay, but you don't always get you don't get a vector back for dot products. So, but you had to do this, right? And you remember it was a very important thing for something to be a subspace, right? And the way you check that was you checked to make sure that it was closed under addition and it was closed under scalar multiplication. So whenever you do the two operations you had there, you get back something in the set. Well, we're saying the same thing here, basically. That is, we have two operations, addition and multiplication, and we're trying to show that if you pick up any two things in there and you perform these operations on them, then you're back in there. Okay? So whenever you have a sub whatever, in algebra, that's exactly what it means. It means that whatever the operations that you have, if you perform those operations on things in the subset, you stay inside the subset. Okay, so this is a very, very general thing, so that's why this is a useful thing for you to get some experience with at the moment. Okay, so that's what we're going to do. So we're going to suppose we're going to pick up two things in here. So we'll call them x and y. And we're going to show that x plus y is an element of AZ and xy is an element of AZ. Okay, again, that's what it means to be closed under these operations. If you pick up two things in there, you add them, you're back in there. You multiply them, you're back in there. Okay. So, let's start with what it actually means to be in there. since x and y are in a z, what does that tell us? Here's our definition right there. So we can use this or we can use this. It's a little easier to just jump to that. So what does x look like? Okay, AC. And y equals?
A, B.
Yeah, pick a different letter. And actually, I don't like C and D at all, so I'm just going to say M and y equals AN, where, what about M and N?
Are elements of Z.
Yeah, these are integers. Okay, now, what is it I need to show about x plus y?
That it's in AZ.
It's in there. And what does that mean?
Equals A times.
Yeah, I need to show that it's a times an integer, okay? So hopefully already you're seeing what has to happen here, right? Okay, so this is am plus an. And now what do I do?
Distribute.
Distribute a times m plus n. And I have to do this, and again, this is the same issue with using division, okay? So I'm going to underline this in blue even before I write it down, because you need to remember this, all right? What do I need to say?
M plus N will be integers.
Yes, and why is m plus n an integer?
If they're both integers, and then the integers.
The integers are closed under addition. So this whole thing goes back to the integers being closed under addition, right? And now I'm done. But I'm not done if I don't write this down. Okay, so this is mistake number 2. You may escape using fractions, but then you will write something out like this and you will not say that. I don't care at this point that you write down because the integers are closed. What I want you to do is observe that it's an integer, because if you don't have that, you haven't shown that it's divisible by a. Okay? Okay, so what do we do with xy? Well, that's am times an. And now how do I write that?
A times.
Well, I like that start. Oh, somebody wants to, I didn't hear who it was, but somebody wants to factor out a squared. Why would I do that? What is it I'm trying to say about xy?
It's an element of Z.
Az, which means it can be written as, it's right there, guys, a times an integer. So if I factor out a squared, what am I actually showing? It's in a squared z, but that's not what I'm after. I want it to be an az. So that's why I write it as a times what?
A times N times N.
AMN, and then my punchline, which must be there, where what? AMN is an element of Z. Okay? Does everybody realize that if you factor that A out there and get A squared, you are not proving what you're supposed to be proving. You're proving something different. You're proving it's an A squared Z, but then it's something different. And what we're trying to do is show that it's actually an AZ. It's a true statement that it's an A squared Z, but that's not what we're after. Because we're trying to show this thing is closed under multiplication. So when we multiply things, we have to show they're back in there and not in something else, okay? I mean, it turns out a squared z is actually contained in az, but, you know, that's, again, I mean, then that's an extra step if you wanted to do that, and you'd have to check that. Which is actually something you will do in your homework. By the way, you know, if you try to do, I've seen students try to do this sort of thing with fractions again, and so then you end up with something like, you know, x over a times y over a equals xy over a squared. And then what are you going to do, right? Then they go, well, I got an a squared and I need an a, okay? So you run into the same kind of problem with that, okay? So just, you know, it can be done. But then you have to worry about the case when a equals 0, so just don't even think about that, all right? By the way, what if a is equal to 0? What is az?
0, 0.
Be more precise than that. More precise, what is it? Sorry?
Set contains z.
It's not equal to 0. What is that? What kind of an object is that?
Just set.
It's a set, so it can't be equal to an element.
So it's the set contains.
Yeah, it's a set containing 0. Okay.